Okay. Okay, it's a pleasure to have Francesco Zamponi from École Normale giving a seminar whose title you can see. Okay, Francesco, it's all yours. Go ahead.
Okay. So thank you very much. Thank you very much, Joel, for inviting me to give a seminar in this series. It's really nice. I'm very happy to be able to talk I mean, this is a very, very nice seminar series that I follow as much as I can, and there are very nice speakers, so it's an honor for me to participate in this. I wanted to, I was hesitating a little bit about the subject, but then I decided to talk about some work that is not really new. So most of what I will talk about has been done a few years ago. So maybe you have already heard me talking about it. I apologize in that case, but since it's related to the subject of the Nobel Prize that has been awarded to Giorgio Parisi a few months ago, I thought it could be nice to review this work. So I will talk about the progresses that we made on the jamming transition using mean field theory. And so the idea, I will start by introducing the jamming transition, and then I will explain how you can construct a theory of this transition using mean field theory. And I will then discuss an application, which is the calculation of the critical exponents of the transition. And then if I have time, but probably I will not have time, I will talk a little bit about the connection with the packing problem in large dimension, and maybe I will give you some technical details on the solution if I have time and if you're interested. Otherwise, I'm happy to discuss the details in private at any time. If you write me an email, I'm happy to discuss. And of course, please interrupt me at any time if you have questions or if something is unclear. Let me know. I'm happy to stop and answer. Okay, so I will start by defining the jamming transition. The jamming transition is very easy to define mathematically. So you take n particles in a periodic volume, for example. I mean, you don't have to use periodic boundary conditions, but let's do that for simplicity. So we have a periodic volume, we have particles in position xi, and we put some kind of repulsive interaction between particles that also has a finite range. So if two particles are sufficiently far away, they will not interact. And then what you do, you initialize the positions of the particles at random uniformly in the box. So let's say you start at infinite temperature. So the particles can be everywhere in the box. And then you run a gradient descent in order to minimize the energy. So the derivative of x is going to be equal to the force, which is minus the gradient of the potential. And the potential is the sum of the pair interaction over all particle pairs ij. And so what you see when you do that, for example, I mean, this has been done numerically in this paper 20 years ago. What you see is that when the packing fraction is low enough, so the packing fraction is the fraction of volume that is covered by the spheres when they are not overlapping. So if the packing fraction is low enough, then at the end of the gradient descent, you end up in a state which has zero energy, and so all the overlaps have been removed. So particles are not overlapping, and the system is mechanically floppy because there are no overlaps. So if you try to deform the system, then you will not have any. You don't. I mean, you can deform the system by applying essentially an infinitesimal force on it. On the other hand, if the packing fraction is large enough, at the end of the gradient descent, you are in a minimum of the potential energy, which is at finite energy. So you have overlaps, so particles interact. And now if you try to deform the box, the system will respond by a finite force. So you need a finite force to apply a finite deformation. The two phases are separated by a sharp transition. So you can do these at different sizes, and then you can do a finite size scaling. And you can show that in the thermodynamic limit, you have a sharp phase transition separating these two phases. And at the transition, the particles are just touching at the end of the minimization. And you have a network of contacts that is mechanically rigid, but particles are just touching. And okay, this...
When you say a sharp transition, you mean as a function of density? Yes,
as a function of density. So this happens in 3 dimensions. This happens at the density of, at the packing fraction of 64%. So for any packing fraction below 64% in the thermodynamic limit, you get to 0 energy. And for any packing fraction above 64% in the thermodynamic limit, you have a finite energy and you have overlaps.
What's the potential between the particles for this?
So the potential is actually not particularly relevant as long as it is repulsive and it has a finite range. But in this numerical study, they used an harmonic repulsion that I will define a bit later. But they also tried other potentials. And I mean, the transition is only driven by the geometry of the problem. So what happens when the particle overlap is not very important. The only important thing is that it's a spherical potential. That of course here there is no friction, and that it is repulsive. So whenever particles overlap, they repel. The precise form is not very important.
Thank you.
But I will give you a concrete example of potentials in a few slides. Okay, so. Okay, in this paper, when they discovered this transition, they also proposed, or I mean, asked the question whether this transition coincides with what is called the random close packing of hard spheres, which is a slightly different problem. So you take hard spheres, so they cannot overlap now. You put the spheres kind of randomly in a box, and you ask what percentage of space is covered by the spheres, like in this case. And this is something that has been studied a lot since, I think, at least the 60s, in particular by Bernal. And we know that if we pack spheres at random in a box, then the volume covered by the spheres is around 64%. So the fact that it coincides with this number was, I mean, suggested that the two things could be identified. And then there was, I mean, if you look to the paper, then there is a comment to this paper where, I mean, there was a discussion associated to this problem of identifying the jamming transition with random close packing, and I will maybe come back on it later, but it's not the main subject of my talk. So for the moment, I will just define jamming as this transition from 0 energy to positive energy in gradient descent for soft spheres. Okay, so now in the same work, they realized that this transition has critical exponents associated to it. So, for example, here you have the pressure as a function of packing fraction. I mean, this is above jamming, so in the phase where particles are overlapping. So there is a pressure. The pressure is the average force that the particles are exerting on the walls. And since there are overlaps, there are repulsive forces, and so you have a force on the walls. So you can define a pressure. And what they found, so here it's above jamming. So phi c here is phi j is the jamming point. And this is a log-log plot of pressure versus the distance to the critical point. And you see that it is a power law. So in particular, so here the two values of alpha correspond to two different choices of potential. So this is a harmonic potential that is quadratic in the distance. I mean, the repulsion is quadratic in the overlap. And this is a potential with another exponent. And you see that you get different exponents that depend on the potential, but in any case, you get the power law. So if I focus on the case alpha equal 2, which is, I mean, just as an example, I will focus on for the rest of this talk, then the pressure is linear in the distance from jamming. So the pressure is 0 below jamming, and then it is linear, is growing linearly above jamming. Now, the other thing they realized in the same work is that there is something very interesting happening in the connectivity of the network of contacts of particles. So, and it's the following thing. I mean, if you think to the mechanical equilibrium equations, then what you want is, because you are at zero temperature in the, you are minimizing the energy by gradient descent. At the end of the minimization, the force acting on a particle is going to be zero. And the force acting on a single particle is given by the sum over all the particles that are interacting with that one of the pair force. And since the potential is a spherical potential, the pair force is radial. So you can write this as the sum over the neighbors of a particle I of some scalar number Fij, which is the magnitude of the force, times the vector that connects the centers of the two particles. Now, if you think that you are given a packing, so you know the coordinates of all the particles, then you know the vectors that connect the centers of the two particles, and suppose that you have to find the forces. Now, the forces are, of course, the forces are, sorry, just one second. Sorry, my daughter is at home for COVID reasons, so, okay. Sorry, I was saying, so suppose that you are given the particle coordinates, and you have to determine the forces. So of course the forces are determined by the potential, but you can think that you have this system of equations and you want to find scalars that satisfy these equations. Now, if you are given the packing, then you have, these are linear equations in the forces, and you have d times n equations, because each component of the force on each particle should be zero. So you have, for example, in 3 dimensions, you have 3n equations, and the number of variables that you have is equal to 1 variable per contact. So if you call z the average connectivity of one particle, then the total number of links that you have in your packing is going to be given by I mean, you have to multiply z by the number of particles, but then you have to divide by 2, because then you are counting each link twice. So, so the number of variables that you have is z times n divided by 2. And so you see that if these are linear equations and you have zn times 2 variables and d times n equations, in order to have a solution, you need to have more variables than equations in the general case. And this happens when the connectivity is bigger than 2D. So for example, in 3 dimensions, it's 6. And this is a special number that is called isostatic number. And what was realized in this paper is that below jamming, so when you are in this phase, the number of contacts is smaller than 2D. You have, I mean, in this drawing, it seems like you don't have any contacts, but in reality, you have some contacts, because you start in a random state, so you have overlaps, then you minimize the energy, and the minimization will stop when particles are, some particles are still in contact, just in contact. So the number of contacts is going to be smaller than 6 below jamming, and it becomes precisely 6 when you reach jamming. And then above jamming, it increases above 6 as a square root of the distance from the transition. So there is a singularity in the connectivity of the network happening exactly at the transition point. And this is a log-log plot of the growth of z above the critical value, which is 6 in this case, as a function of the density increase above the critical density.
So phi is essentially a volume.
Yes, phi is the density, the number density multiplied by the volume of one sphere. So it's the, I mean, if phi is equal to 1, then all the volume is occupied by the spheres, and otherwise it's the fraction of volume that is covered by the spheres. But I mean, you can think that it is essentially the number density. Okay. Okay, the other thing that was noticed soon, I mean, shortly after this jamming transition was introduced, people realized that there is a diverging correlation length that is associated to this transition. And one way of seeing this divergent length is the following. So you start by preparing a packing at some pressure. So pressure is proportional to the distance from the transition. So 0 pressure is the critical point, and then otherwise, like here, pressure 10 to the minus 2 is a relatively high pressure above the critical point. And here is 10 to the minus 6, so it's much closer to the critical point. So you start by creating a packing by minimizing the energy. Then you take a particle, for example, in the middle, and you displace it a little bit. And now you re-minimize the energy, and you look to the variation of forces in the packing. So here, when you see a red link, it means that the force has increased. When you see a blue link, it means the force has decreased on that link. And what you can see is that at pressure 10 to minus 2, if you perturb the system locally, the response is relatively local too. But at pressure 10 to the minus 6, so when you're very close to the critical point, you perturb the system in the middle, and the response extends essentially to the full system. You have these force chains that extend everywhere. So you can define a correlation length by looking at the size of this, at the decay of this force field around the perturbation. So it's a kind of a response measurement. And they found, by doing that, you can check these papers, for example, they found that the correlation length scales as the inverse of the square root of the pressure. So when pressure goes to 0, you reach the critical point, the correlation length diverges. And you can also see that if you look to the vibrational density of states of these packings, when you decrease the pressure, you get more and more low frequency modes. So these different curves are at different pressures, until when you reach 0 pressure, you have a lot of soft modes. So you also have a typical frequency scale that goes to 0, that is associated to the stability of these excitations.
What's the exact definition of d omega?
So you take the, okay, so you minimize the energy, you create a packing, and now you are in a minimum of the potential. So you can compute the matrix of second derivatives of the potential, the Hessian matrix, and then you can diagonalize this matrix, and this is the density of states of the eigenvalues of this matrix. So it's the density of the vibrational modes of your system, of frequency omega.
Thank you.
Okay. Okay, so you can also define other length scales. For example, you can look to the correlation of the contacts. So you can take a particle here, you count how many neighbors it has. You take a particle away a distance r, count the neighbors. You do the correlation of this connectivity field. And this also shows a divergent correlation length when you approach the phase transition. And you can check this. Yes?
Are those results numerical?
Yes, up to now, everything is numerical.
Thank you.
Okay, so this transition is associated to some spatial correlation that is divergent. It is also associated to a time scale that is divergent. And to see that, people have done, again, numerical simulations. And okay, I told you that in order to define jamming, you start from an initial state that is a random state at infinite temperature, and then you minimize the energy by gradient descent. So this is the energy as a function of time during the gradient descent minimization. So when density is low, for example, 0.6, you see that you get exponential decay at long times. Now, when you increase the density, you see that the decay becomes slower and slower until when you reach density around 64, you don't see exponential decay anymore. You start to see a power law that emerges. And so you can fit this data by exponential curves below 64, below jamming, and you get a time scale. And you can plot this time scale as a function of the, here is the distance from jamming measured in terms of the average connectivity, but you can do it using any other, for example, density or pressure. And you see a power law divergence of this time scale, okay? So, and the power law as an exponent, and you see that the exponent is about 3, and it is more or less the same in all dimensions 3, 4, 8, but it is slightly different in 2D. There seems to be something special in 2D, and I will maybe come back on that. Anyway, the important point is that you have a divergent relaxation time, and this is the time it takes to the gradient descent to relax to the final state. So this time is going to diverge at the jamming transition. So in this sense, jamming is really a phase transition in the usual sense. It's associated to a divergent correlation length, a divergent time, and to divergent fluctuations. However, it is a kind of it's a kind of unusual phase transition because it happens at 0 temperature and also out of equilibrium, because here we are starting from infinite temperature and we are doing 0 temperature dynamics. Essentially, we are just relaxing the energy to a minimum. So the system is not at all able to equilibrate at any temperature. I mean, it's really a totally out of equilibrium phenomenon up to this point. Okay, so from now, I mean, up to this point, I described mathematical definitions and numerical results, but actually this jamming phenomenon is something that happens in many real life contexts. For example, in granular materials, like for example, here you have an experiment from the group of Bob Beringer using disks in 2 dimensions. So these disks are photoelastic. So whenever you have a force on the disk, you get light. So you can shed light on the system, and you can measure where are the forces. And you see that you have force chains that are extremely heterogeneous. This is very, very close to jamming. So it's more or less the same kind of picture that I've shown here in an experiment. And this is very important because this means that the force that you have locally in this kind of packing is very, very heterogeneous. And so, I mean, this can lead sometimes to spectacular failure, like in packings of grains, you can have strong fluctuations and sometimes this can lead to collapse. And also you can play with it. So this is a board game that you can find in the office of Olivier Dauchot in Paris. So the game is very simple. There is a piston here, and you have to remove the discs. So each player has to remove 1 disc without moving the piston. So if you are, I mean, if you are lucky, basically, because it's very hard to predict where are the force chains, but if you are lucky, you are going to remove a disk that is in a floppy region. So you remove the disk and nothing happens. But if you are unlucky, then you are going to remove a disk that is part of a force chain, and then the packing will be destabilized and the piston will move. Okay. Okay, so these are examples, but I mean, there are many other examples of real life manifestation of this kind of phase transition. Okay, so what I would like to emphasize to finish my introduction is that on top of being a non-equilibrium phenomenon, it's also something that happens in a disordered system. So the particles are in a disordered state and they stay in a disordered state, and it's not clear how to find some kind of symmetry breaking associated to this transition. So it's hard to use conventional tools that we use to describe phase transition and equilibrium. And the other thing I would like to mention, but without describing it really, is that this transition that I introduced in the context of granular materials is also something that happens in computer science, and in particular when you have a constraint satisfaction problem with continuous variables. This is essentially what is called the SAT-ANSAT transition for those who know these kind of things, or what is called the capacity transition in data classification problems in machine learning. And so if you are interested in this connection, you can check, for example, this paper where this is explained. And I'm also happy to discuss it privately, but I don't have time to describe this in details today. Okay, so now I would like to explain how we can try to construct a theory of this phase transition. And this is something that we try to do by using a very old, let's say, approach to phase transition, which is to start with sending the dimension of space to infinity. So I showed you results in 2 dimensions and in 3 dimensions, but we can take 4 dimensions, 8 dimensions, 10,000 dimensions, infinite dimensions, and we can hope that things simplify when dimension is very large. And this is something that happens in many fields of physics. And this is a nice review. But I also wanted to mention a few other examples that I like. So there is, okay, I think one of the first papers where I've seen this approach is this paper by Fisher and Gaunt, where they studied the critical temperature in the Ising model using a 1/d expansion. There is also nice work on QCD in large dimensions. In this paper, they applied it to liquid theory. So they showed that the virial series becomes much simpler in infinite dimension, and you can drop many, many terms, and essentially you can solve the problem exactly and compute all the thermodynamics of the liquid in infinite dimension. And then there is, I think, this important work of George and Diedidia on spin glasses, where they set up a 1/d expansion for spin glasses. And then they also, Antoine Georges and other people, they followed up constructing a theory of correlated electrons, which is known as the dynamical mean field theory, or DMFT. And it has been extremely successful to describe correlated electrons in using, again, a 1/d expansion. So this is something that has been a kind of recurrent theme in statistical physics. And in the context of glasses and disordered systems, this is something that has been proposed in a very beautiful paper by Kirkpatrick and Volines in 87, where they took some theories that at the time were considered to be standard microscopic approximations for glasses, and they showed that in infinite dimensions they become consistent, and they constructed a kind of a consistent first principle theory of the equilibrium glass transition in this infinite dimensional limit. And okay, my original motivation to look at this problem together with Giorgio Parisi was to understand the problem of sphere packings, which I told you is related to this problem of jamming, but is slightly different. And what we did in these papers was to take the theory of Kirkpatrick and Volines for glasses and adapt it to the problem of to the case of hard spheres, and then study the problem of random close packing within the theory. But this is not what I'm going to discuss today. What I want to discuss today is the jamming transition. So I told you the jamming transition is a kind of out of equilibrium dynamical phenomenon. So I start at infinite temperature, and then I minimize the energy by gradient descent. So if I want to investigate this transition by a kind of a brute force approach, what I have to do is to solve the gradient descent dynamics in infinite dimensions. So I have to take these equations here, derivative of x equal to gradient of the minus gradient the potential. This I can write in any dimension. I can try to see if in infinite dimensions I can simplify the problem somehow and make it solvable. So this is what we tried to do in a series of papers, starting from this one, together with Thibaut Membour and Jorge Kurchan, where we show that in the limit of infinite dimensions, you can, you can apply kind of mean field theory that is dynamical, and it's very similar actually to the dynamical mean field theory of quantum systems. And so you end up with a single one-dimensional stochastic differential equation, which is stochastic because the interaction basically describes a single particle in the mean field of all the other particles. And it is stochastic because the interaction with all the other particles is represented by an effective stochastic noise, as usual. The problem is that the noise is a colored noise. It's correlated in time. And it is not given. It has to be determined self-consistently as an average over this one-dimensional equation. So it's the usual mean field structure where you have a representative degree of freedom that is evolving in the mean field of all the others, and you have to set up a self-consistent equation to fix the unknown terms in the BAT, let's say. So this can be done in general. This is we believe it's exact. I mean, it's not rigorous. We cannot prove this rigorously, but for the standard of theoretical physics, we believe that it is under control. The big problem is that you end up with these equations that are one-dimensional. So you don't have to take any more the thermodynamic limit. You simplify the problem quite a lot, but still the equations are very hard to solve. So we tried, I mean, this is a paper that we posted on Archive 2 weeks ago, where we tried to solve these equations numerically, and we could solve them for relatively short times, but if you try to extract the asymptotic long time solution, it's numerically, it's very, very, very difficult. We could do something analytically. We could derive, for example, the form of the kernel that describes the noise and things like that, but we were not able to extract the critical exponents from this approach. So unfortunately, for the moment, this is what would be the simplest approach, but it's not working because the equations that we get are very, very hard to analyze.
Are you going to show the equation actually?
Sorry?
Are you going to show the equation?
Not in the talk because they're not very beautiful, but I can, if you want, I can open the paper and I can show you later.
Yeah, maybe at the end.
Yes, I'm happy to show at the end if you're interested. I mean, they are not very, I mean, I think putting them on the screen would not be very instructive because they are a bit complicated, but I'm happy to discuss them later. So anyway, they are also in the paper. So if you can also check, they are written there, but I will show later. So, okay. Okay, so this brute force approach for the moment does not work. Of course, if someone has any idea to solve this problem, we would be extremely happy. But so since this doesn't work, for the moment, I will describe a kind of smarter approach, but that requires kind of a conceptual detour. So it's a bit more complicated to explain, but it's nice, and I think it's very smart. So and it works. So I wanted to describe it. And this is the idea of following adiabatically metastable glassy states out of equilibrium. So I will explain that, but I just want to say that it is an idea that comes from the early work of Kirkpatrick and Tirumalai, and also more recently, I would say, of Monasson, Franz Parisi, and Mézard and Parisi. So it's a kind of machinery that has been developed over the years in the field. So how does it work? So I'm sorry, at this point I have to do this little conceptual detour that, and I hope that I will be able to explain the idea. I will not give all the details, but I will try to explain, I mean, the physics of it. So let's take, for concreteness, let's take a particular model, which is the soft sphere model. So this is the example.
Can I ask a question quickly?
Yes, yes.
Yeah, you put, are you still using D goes to infinity limits?
Yes, yes.
Okay, so
I will,
there's that very unphysical aspect of it still.
Yes, 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 of course. I will, for the moment, all the analytical theory is going to be done in infinite dimensions, and then I will show you how it compares with numerics in 3D, in 2D. But yes, yes, this is always, I mean, for the moment, I will stay in this unphysical limit of infinite dimensions. So, okay, so this is an example of potential. It's a potential that is 0. Oh, I'm sorry, this is there is a minus sign here. It's theta of sigma minus r. So this potential is equal to 0 when r is bigger than sigma. So the particles do not interact when they are separated by more than sigma, and otherwise they repel, and the repulsion is quadratic in the distance, in the overlap between particles. Okay, so this is a model of pair potential. So this, I hope this answers Joel's question from before. And we can study this model. So if you study the liquid theory of this model, there are two parameters, the temperature that you can express in units of the energy scale here, and the density, which is this phi here, that I will rescale in this way in order to have a finite quantity when the dimension goes to infinity, but this is just a constant rescaling. And okay, of course, if you take this model and you send epsilon, the energy scale, to infinity, or you send t to 0, then you recover hard spheres. Now, if you study the phase diagram of this model in the limit of infinite dimensions, then you get a glass transition line that separates a regime where so now I'm studying the equilibrium dynamics. Okay, so I take a state point, some temperature and some density, and I study the dynamics in equilibrium. So if temperature is high enough or density is low enough, then you get diffusive behavior. Otherwise, you get arrested behavior, which means particles remain kind of localized in a certain region, and they cannot diffuse. So this is an equilibrium glass transition that only happens strictly in infinite dimensions. It doesn't happen in finite D. It's a huge field, and there is a huge debate about the nature of the glass transition in physical dimensions that I'm not going to discuss. I just want for the moment to stay in infinite dimensions. The important point
in infinite dimension, is this an exact result?
Yes, in infinite dimensions, it is an exact result in the sense, I mean, again, unfortunately, it's not a rigorous proof, but I think we have all the errors under control from a theoretical physicist point of view. So I think I can say it's an exact result. And I mean, also, if you do numerical simulations and you increase the dimension from 2, 3, 4, 5, and you can simulate up to 12, I mean, you see that the things become more and more consistent with this prediction. So it should, it should work. Now, the important technical point is that when you are in the arrested phase, you can use a general correspondence between dynamics and replicas that you have in disordered systems that has been studied a lot in spin glasses and related systems. So essentially, you can rephrase the long time limit of the dynamics in terms of a replica construction. I don't have the time to enter into the details of that, but again, I'm happy to discuss it privately with whoever wants to know more. But okay, the idea is to exploit this because, I mean, solving the dynamical equations, as I told you, is very difficult. And for the moment, we are not able to do that. But in this arrested phase, we can turn the problem of solving dynamics into a problem of replicas, and that we can solve. So what is the idea then? I told you that in the original jamming transition, the problem was to, the mathematical setting was to prepare an initial state at infinite temperature and a certain density, and then run gradient descent to minimize the energy. So what what I can do, I can repeat the same thing, but instead of starting from an initial state that has been constructed at infinite temperature, I can prepare first an initial equilibrium state at some temperature, and then from there, I run the gradient descent. So let me draw this in this phase diagram. So this is temperature, this is density. Suppose that I start by preparing an equilibrium state, for example, here, in this point. I think you can see my mouse. So let's say we are in this point. I can equilibrate the liquid here, and then I can stop the dynamics. And then now from this configuration that I have, that is an equilibrium configuration, I can run gradient descent, and I can check if the final state is jammed, which means the energy is finite and I have overlaps, or if it is unjammed, which means that I have zero energy and no overlaps. So what if you do that, and this has been done, again, it can be done numerically, but also analytically in this infinite dimensional setting, what you find is that there is another phase transition line, that is this line here, the dashed line, such that above this line, you get jammed jammed states when you do this. while below you get unjammed states. So you see that if you cross these two lines, this is the equilibrium glass transition, and this is the jamming transition, you obtain 4 regions in the phase diagram. So let me describe this again. If I'm here, I prepare an initial equilibrium state, and the system is in the liquid phase, so the equilibrium dynamics is diffusive. And then when I take a typical liquid configuration in equilibrium and I minimize the energy, I get a jammed state. If I'm here, the equilibrium state, the equilibrium dynamics is diffusive, but when I minimize the energy, I am unjammed. And okay, the jamming protocol that I described initially is the particular case when the initial temperature is infinite. So I am on this line up here. So the jamming point that I described before as a function of density is the asymptotic, the asymptote of this line when temperature goes to infinity. I hope this is clear. Now the point is, if I'm at low temperature in this region, the equilibrium state, the equilibrium dynamics is arrested, so I get a glass. And then if I minimize the energy of this, I get a jammed state. While here I get an unjammed state. So I can describe the jamming transition here, where the problem is, maybe counterintuitively, the problem is easier because I can use the replica method. I don't have to solve the dynamical equations that are unfortunately complicated to solve technically. And so from the replica method, I can describe what happens here. And in particular, I can describe this phase, phase transition in this region. Not in this region, unfortunately, but this should be done by solving the dynamics. Now, the important point is that when people do this numerically, they see that the critical properties of jamming seem to be universal on this line. So the critical exponents are the same. So if I can compute something here, I can hope that it also works on the other side. But this is an extrapolation. Okay, the last ingredient that I need before I show you a few results and I conclude is something that is called the Garner transition. And so the question, what we did is with these people here, Patrick Charbonneau, Jorge Kurchan, Giorgio Parisi, and Pier Francesco Urbani, was to try to carry on this program. So try to use the replica method to compute the jamming line in this region and study the critical properties. But what we realized is that there was one missing ingredient. And okay, we have a book that is recently published where everything is detailed in case you are interested in the details. And the missing ingredient is that when you take, so if I start here, I told you I have a system that is in equilibrium but is arrested, is non-ergodic, so it's a glass. So you are stuck in this glass in equilibrium. Now you try to cool, you try to minimize the energy, so you try to bring the system rapidly to 0 temperature. And so here is a diagram of energy versus temperature for a given density. So I start from some point here in the glass phase, I go down, and I see that there is a phase transition inside the glass phase. And this phase transition is of the same universality class as the spin glass transition that you see in the Sherrington-Kirkpatrick model. So it's a phase transition between a replica symmetric phase and the full RSB phase. And this is something that was discovered first by Elizabeth Garner in '85 in spin glasses, and that we kind of rediscovered in the context of this infinite dimensional glass phase. Anyway, I'm sorry that I cannot really enter into the details because it would take a lot of time, but the main message I wanted to communicate is that we cannot attack the problem in this region. We can use replicas, but when we use replicas, we realize that we need full replica symmetry breaking to describe this jamming transition. Now, what do we get? What we get is that there are critical exponents. I already described some critical exponents. Let me introduce a few others that are important. So the first thing is that when you are in the glass, I told you that the dynamics is not diffusive because you are in a glass. So the mean square displacement of a particle goes to a finite plateau. which is the Debye-Waller factor of your solid. And now when you go to jamming, because particles are at 0 temperature and they cannot move anymore, this value goes to 0. And it goes to 0 proportionally to the temperature to some power kappa. So this critical exponent kappa is going to be important. The other thing is that when you are at 0 temperature and you are at jamming, you can define the distribution of gaps between particles and the distribution of forces between particles. I will show you, I will come back to this later in a second, but these two quantities behave as power laws, and there are two critical exponents, gamma and theta, associated to these power laws. So there are three critical exponents, kappa, gamma, and theta, that are very important, and these were identified by Mathieu Viard in this nice work. And so what he did in this work was to introduce these exponents and also show that the fact that the system is kind of marginally stable at jamming implies scaling relations between these quantities. So you have scaling relation between gamma and theta and kappa and theta. So you have only one exponent, theta, that remains undetermined by the scaling theory. So if you do, sorry, this is a typo, the replica symmetric solution. So if you neglect full replica symmetry breaking, you get wrong results that are inconsistent with numerics. If you take into account this Gardner transition to full RSB at low temperatures, then you get non-trivial exponents that are given here. And these exponents are consistent with the scaling relations that were derived by Viard and co-workers. So how do they compare with numerics? So these are some numerical results. This is the exponent kappa. So you take your glass, you take your packing of spheres at some temperature. So here, this is pressure over temperature. Sorry, there is a temperature missing. So you can change temperature or you can change pressure, is the same. But let's think that you have a packing of particles at some temperature. You lower the temperature and you measure the amplitude of the vibrations of your particles. And this goes to 0 when the temperature goes to 0. And when you are at jamming, you see these are results in 3 dimensions, 4, 6, 8. It's basically independent of dimension, and it is consistent with the value that is P to, that is, okay, here is pressure, but I mean pressure to the minus kappa with this value of kappa. So this is good. Here I also report the value of 3α, which is very close. It's 1.5 instead of 1.41, because in the beginning, people, based on the numerics, they thought that the exponent was 3α, but then, we could show that it's not exactly 3α, and numerically we can kind of distinguish the two. But okay, maybe easier to measure is the exponent of the gap distribution. So this is constructed in this way. You go to jamming, so you go to 0 temperature, you go to the jamming density, particles are just touching. Now you can take pairs of particles and you can measure the gap between them. So this is for pairs of particles that are not in contact. So for contacts, you have 0 gap, but for the others, you have some gap. You call the gap H, or it's R divided by sigma minus 1. You do a cumulative histogram of these gaps, and this is how it behaves. This is numerical simulations in dimension 3, 4, 5, 6, up to 10. And you see that you get the power law at small gaps. And the blue line is the prediction of the full RSB approach, which gives you gamma, an exponent gamma here equal to 0.41. And finally, you can take particles that are in contact. You can measure the force. So when you are exactly at jamming, the force is 0 because they are just touching. But you can go slightly above. You can scale the forces by the mean. And when you go to jamming, the limit of the force divided by the mean force, they both go to 0, but the limit is finite. So you can take all particle pairs, you compute this quantity, the force divided by the average. You do, again, a cumulative histogram, and you see a power law region. And the red line, again, is the prediction of the full RSB calculation. Here, this effect is due to the finite size of the system. So if you, the latest numerical results can be found in this paper from last year, where they did finite size scaling with very big systems with very, changing dimension, and they basically found that these exponents are independent of spatial dimension. So, so let me summarize. So you can obtain the critical. You can obtain predictions. I also forgot to mention that I also introduced other exponents. For example, this exponent here for the pressure, the exponent for the pressure, and this exponent 1/2 for the contacts, and so on. And all these exponents can be obtained from the full RSB solution. What is missing? So let me try to summarize. So we can basically obtain all the critical exponents using this idea of following adiabatically the system in the region where the dynamics is arrested. And so we can kind of replace the dynamics by the replica. It's a kind of convoluted approach, which is maybe not necessary, but it's the best we can do for the moment. And if we do that, what we find is that in order to apply the replica method, we need to use full RSB. And then we get non-trivial critical exponents. When I say non-trivial, I mean that these exponents gamma, theta, and kappa, they are not simple rational numbers. Maybe they are rational, but we couldn't, we have to solve, we obtain them by solving numerically some partial differential equation. We didn't find the solution with simple numbers. So you see that these are numbers that we can compute them as precisely as we want, but they don't seem to be equal to some simple value. And so this is a bit surprising, because usually in field theory you get exponents that are I don't know, 1/2, 3/2, or things like that. Here it's not the case. And what is also very surprising is that and this I hope maybe answered the question from Jim Langer before, that this kind of abstract unphysical limit of infinite dimension, in this case, for the jamming transition, I'm not claiming it's working for everything, but for the specific case of the jamming transition, it seems to be working very well down to 2 dimensions. Can you hear me well? Because it seems that my internet connection is a bit unstable. So
it seems okay. I can hear you well.
Okay, thank you. So it seems that the infinite dimensional prediction works very well when you compare with numerics down to 2D. And so this is kind of surprising because it's, I think it's also probably one of the rare instances when of full RSB giving really quantitative predictions for critical exponents in finite D. In the case of spin glasses, when you have full RSB, there is a big debate on whether the full RSB solution is still physical in low dimensions. And here it seems to be quite working quite well. So there was a debate on whether 2 might be the upper critical dimension for jamming. So there is a nice work by Daniel Exner and Lucid Nagel, and we also have a follow-up on that, where we try to check if 2 is the upper critical dimension using ideas from finite size scaling and so on. But it's a bit hard because this jamming transition, as I told you, is a non-equilibrium transition in a system that is disordered and so on. So it's hard to, at least for me, it's hard to frame the problem in terms of some kind of field theory. So then it's hard to do like an expansion around the upper critical dimension. So, one can try to argue based on numerics, but it's not, I think it's an open problem to define an upper critical dimension for this transition and compute it. So I think I will skip the connection with the large D problem, and I will also skip the details. I just want to mention one thing, that is that the reason why we get non-trivial exponents is because in the full RSB approach, the order parameter is a function, it's the overlap probability distribution. I think you heard about it. And so the fact that the order parameter is a function means that it is determined by a differential equation. And in the scaling limit, this differential equation has, becomes some kind of, you have to solve a boundary problem, and then you get these exponents that are fixed implicitly by this boundary problem. So it's not a simple like Landau kind bifurcation. And so that's why you get non-trivial critical exponents. So with this, I conclude. I just wanted to quickly summarize. So I think jamming is a source of a lot of beautiful mathematics. It is connected with many problems in soft matter physics and also in computer science. And it seems to be defining some new universality class that can be described by full RSB. And so I think that's why I wanted to discuss this today, also because I think, in connection with the Nobel Prize that was given to Giorgio Parisi last year. What I would like to do in the future is to try to rederive all this without going through the replica approach, just by dynamics. And if one can do that, it's probably, more like easier to understand without having to go through the tour of introducing the glass and so on. So thank you for your attention. And
thank you very much. Let's unmute ourselves and give an applause to Francesco for a very, very nice talk. And I think I'll open it for questions. Francesco, maybe you're going to stop share your screen so you can see people if they ask any questions. Okay, are there any questions?
Yeah, quite early in your talk, you showed that 2D was behaving differently for some quantity than higher dimensions, but then you didn't come back to that at the end. So can you revisit that?
Yes, I'm sorry, I forgot to mention that, yes. So there is one exponent that is not, what works well are all the exponents related to the static quantities. So I told you, we get correctly the exponents for the pressure, for the average coordination of the packing, and also for the gap distribution, force distribution. What is not, for the moment we cannot compute is the exponent that characterizes the time, the relaxation time. So the relaxation time diverges when you approach jamming from below. So when you are in the unjammed phase, you have exponential relation to exponential decay of the energy to zero, and the time, the rate of the decay goes to zero, or the time goes to infinity when you approach the jamming point. And this is associated to an exponent that seems to be slightly different in 2D. And there is some debate in the people who are doing the numerics on whether this is really a robust effect. So is there something special in 2D? That's why some people think that 2D could be the upper critical dimension. And maybe there is some logarithmic correction. It's not totally clear, but in any case, the problem is that unfortunately, for the moment, we cannot get this exponent from the mean field theory, even in infinite dimensions. And the reason is that we cannot solve the dynamics. So we can solve this, we can map the dynamics into the statics at long times using this replica trick. But then we lose this time relaxation. And so I don't know, any idea on how to solve that would be very welcome. And also because this exponent seems to be non-trivial. And there is some argument from Mathieu Viard again, who related this exponent to the exponent theta of the forces that I introduced at the end. And so it would be nice to derive that from the mean field theory, but
so at this point, this is gradient descent dynamics, presumably?
Yes.
And then when you later you went to a model at non-zero temperature, was that just adding a Langevin term to the gradient descent, or were you doing Newtonian dynamics, or what kind of dynamics were you doing?
you can, it's actually not very important because you want to look at the long time limit, but the idea is you do, for example, you can think that you do Langevin dynamics with some noise term at some temperature. You do it for a very long time. You let the system equilibrate at temperature T. And then at some time, you switch off the noise and you do gradient descent.
Yeah. Right.
Okay.
No, but you
So
had
first,
a glass transition line,
yes,
which
so,
does that depend on the dynamics?
no, that one, I mean, at least in the mean field theory, doesn't depend on the dynamics as long as you have a dynamics that satisfies detail balance, because it's a kind of a long.
So it has to be a stochastic dynamics.
No, it can also be, sorry, it can also be Newtonian. I mean, I mean.
Okay, so it would be the
as long
same
as
for Newtonian or stochastic. Okay,
Yes, yes.
thanks.
But the point is that you have first to equilibrate, and then at some point you switch off the noise and you let the system relax by gradient descent. So you're changing.
Well, that's
the
to look at the
state.
jamming transition. I'm talking about the
that's
glass
look,
transition.
Yes, I don't know. Yes,
Glass
of course,
transition, you don't switch it ever off.
Yes, exactly.
And
But then the glass
you're saying
transition.
that's independent of the dynamics you choose.
Yes, but then the glass transition is something that is a sharp transition in infinite dimensions. But when you go to 2D or 3D, it becomes much more complicated.
Yeah.
So what is kind of surprising is that we go through the glass transition to get the jamming. We know that when we add fluctuations in finite dimensions, the glass transition is destroyed, but still the jamming transition seems to be correctly described by the mean field, which is a bit strange to me, but okay. So there is something to be understood.
Are there any other questions?
I have a question.
Go ahead.
So you're doing all of this with spheres. It's been known, work by various people, that if you use ellipsoids of revolution instead of spheres, the behavior becomes significantly different because the counting of degrees of freedom is different. So can any of this be applied to the other problem?
Yes. So we have some papers from a few years ago where we extended this to ellipsoids, and you are right. In that case, the universality class of the transition changes. So you get different exponents, which okay. So somehow the spherical case is a bit special. So I mean, if you perturb a little bit the shape and it's not perfectly spherical, then you get a different universality class. Yes, but well, so it can be extended to, I mean, the same approach. I mean, you have to define ellipsoids in infinite dimensions, but I mean, basically you can take, for example, something that is spherical in all directions except one, and then you can redo.
That's called an ellipsoid of revolution. Yes.
Yes, exactly.
Any other questions or comments? Maybe I'll get back to my original question. You want to show the actual stochastic equations that you try to solve?
Yes, just give me a second. I will do that. So let me share the screen again. Can you see the paper?
Yes.
Okay, let me zoom a little bit so it's more visible. So, okay, so the idea is we start from gradient descent. So x dot equal to minus gradient of the potential, and then okay, we do this mean field and we get to something that has this form. So you here y is the projection of the motion. So basically what you do, you take two particles and you consider two particles that are evolving in the thermal bath that is given by all the other particles, okay? So these two particles are going to interact, and when you go to infinite dimensions, you can show that all the important motion happens along the direction that connects the centers of the two particles. So in the radial direction, not in, I mean, the transverse motion is trivial, is just diffusive. So y is the coordinate of the two body problem along the radial direction, is the projection, sorry, of the motion of the two particles along the radial direction. And you see that you get that y dot, so the derivative of y is given by the gradient of the potential. So this v is just the potential. So this is the original gradient descent. I mean, there are this is the initial condition. This is the contribution of the transverse directions that you get here, and then you get some kind of harmonic force that is bringing it back to zero, and then you get some noise, and you get a friction. So this friction is described by a kernel mr, and the noise as correlation mc, and these two, I mean, if you were in equilibrium, these two would satisfy fluctuation dissipation theorem, but if you're doing gradient descent, they don't. So they are in general two functions, and they are defined by, so you have, now you have three terms that are unknown. You have this kappa of t, you have these two functions, and all these terms are defined by this self-consistent equation. So for example, kappa, so this the effective spring. So this kappa, if you want, is due to the fact that you have two particles that are surrounded by other particles. And so if they try to get far away, they are pushed back by the other particles. So there is some kind of effective elasticity in your medium. And this is defined as an average over this same stochastic process of the second derivative of the potential, basically. Plus there is another term, okay.
Okay.
And for example, the correlation of the noise is given by the force correlation averaged over this process. So what you have to do, so if you want to solve these equations numerically, you have to start with a guess for these kernels. Then you generate numerically many trajectories of y. And then, okay, h is just something related to y. And then you, from this ensemble of trajectories of this y, you can recompute the kernels, and then you have to iterate this process many times until it converges. So that's why it's a bit, I mean, the numerical integration can become unstable. We have a lot of numerical problems. I mean, we're trying to get inspiration from people who do this for quantum systems. They have similar equations, but okay, it's not totally the same. And for the moment, we were not able to solve numerically. And analytically, you can do some things, but you cannot derive, at least for the moment, all the
Thank you very much. Are there any other questions or comments?
Could I ask what the replica symmetry breaking means in the language of the original problem, the gradient descent dynamics? Sorry, maybe.
Yes. So yes. No, I didn't discuss that. Sorry. So what replica symmetry breaking means in this context is that I told you that the way we describe the problem is we first equilibrate at some temperature. So now we get an equilibrium configuration, and from there we do gradient descent. And so we try to describe the gradient descent as a, so if you want, the initial configuration plays the role of some kind of an external field in the problem. It's like if you have a spin glass and you are applying an external field that is decoupling to this initial condition that you have. Now you minimize the energy, and the fact that you have full replica symmetry breaking means that when you minimize the energy, you have a lot of minima that are organized in this ultrametric Parisi structure. So your gradient descent, if you redo the gradient descent and you perturb a little bit the initial state, for example, you can end up in many different minimas that are organized in this complex pattern that is characteristic of mean field spin glasses. Okay, so that's why you have replica symmetry breaking in the problem. So it has some physical meaning, but I didn't have time to enter into all that.
Okay, thanks. Can I ask another quick question, which is, you had one exponent which was simple, which was a half. Do you still need the full apparatus to get this exponent?
Yes. So I don't know exactly why, but when you look at the mathematics of the thing, if you just do replica symmetry, you don't get 1/2, you get 1 instead of 1/2. And when you do the full RSB, it becomes 1/2.
Okay, thank you.
On this, I don't have a physical interpretation. It's just the mathematics of the problem that is like that.
Any other questions or comments? If not, let's unmute ourselves, and thanks again to Francesco for a very, very nice talk. Thank you very much.
for joining and for listening to me. Thank you.
Happy New Year. See you next week. Take good care. Bye-bye.
Thank you. Bye-bye.